So you need to run Docker instead. Do you have Docker installed on Mac?
No.
You can run the Docker, and then it's not the image that you need. You just get the tutorial. It's a different image.
I see. Okay.
Okay. Then I can show you how to do that.
Sure. Yeah.
Thank you.
All right, let's continue. So it's the second and the last lecture for me. What is on the board here is a perfect introduction to my lecture, and but I already told George that I feel like a barbarian who came into the ancient Rome. But now the barbarian has to destroy the temples in ancient Rome in order to put some scribbles there, which so here. So little, this is all so true. This derivative we are going to see in my presentation. I will just introduce evolution equations, but they are essentially the same derivatives, some answers for those derivatives. So what the plan for my lecture would be is that I'd like to introduce TMD evolution equations, and then my perfect excuse to actually raise the board is that I'm going to show how Collins-Sofer-Sterman formalism is then derived. So the organization of all terms in what is known as a summation for Collins-Sofer-Sterman. Okay, it's quite ambitious, and I hope we can go through the solve. However, because our lectures are all evolving, therefore, I'd like to contribute to some of the questions that arise yesterday. In particular, we were talking about different signs, and then some of you told, well, wait a second, this is the difference between Drell and serious, and therefore this function has a sign there, and of course I didn't mention anything about this. So let me start and spend a few minutes before I dwell into solution of evolution equations. Let me talk about physical interpretation. So in particular about this, as we're talking about this KT versus T, Fourier transforms, and what I introduced this thing, which was the distribution of unpolarized quarks in a transversely polarized ion. Okay? And this was, I wrote it as F with some subscript gamma plus, which was the trace of the correlator. Okay, so it looked like this. So it's F1 of x AT minus epsilon Tij, okay, KTI STJ divided by M F1 perp of x T. Okay. I told you the scalars and therefore they parameterize. So this is what is known as just unpolarized distribution. Very important, unpolarized distribution, unpolarized quarks, F1, PDF, know that. So now this term here, it has some function. Okay, so with this very strange name, 1T perp. Okay, I will not dwell in telling you why this name is given here. Or I can. Okay, T is the transversely polarized quarks. 1, the leading twist, and perp means that it depends on this KT. So if there is no KT, then this function is 0. If this KT is 0, this will not contribute. Okay. But more so, I'd like you to see the structure of this thing. So this is the transverse antisymmetric tensor times KT times T. This thing is a correlation between the transverse motion and the transverse spin. Okay? Transverse motion and transverse spin correlation, and this thing gives you how much of this correlation, what's the strength of the correlation. This is what is known as series function. First of all, this thing is correlation. As far as it is a correlation, it's not a probability, therefore this can change sign. There are different types of quarks, and we saw that for up quarks, negative quarks, it's positive. Well, more so, if you see it's like the cross product here, and one can say, oh, wait a second, I know about cross products. Okay, orbital angular momentum is cross product. When created by quarks, they are moving different inside of the neutron, right? So it has to be R cross P, R cross P, or R cross K. So I not it as K. So we have K, but we don't have R. R somehow is missing, so I don't know how much of the orbital angular momentum here. And what one can say, oh, wait a second. BT. Okay. Let's take BT there. Is it going to be orbital angular momentum? Answer is no. But the question is why? Why it's no? And the answer is subtle, so I'll just give you some semi-mathematical like description of that. The reason why I was calling this thing BT in configuration parameters, many words, instead of just saying it's an impact parameter, it's important because words matter. Okay? So this is not an impact parameter, but the question is, what is impact parameter? So, words. Therefore, let's go back to just our drawing. This drawing is important. Therefore, just a few next minutes. Okay, so this drawing is our correlator, which actually incorporates all our functions that we study. It's a correlator with particles, with the imaginary part for this. So there are fields. This sits at some position B, and transverse position is important. That's why BT. Okay. It has some other component, which is Fourier conjugate to X Bjorking, which I didn't pay much attention here, but more strict. Okay, and this is sitting at some position 0 in space. So those are fields. So I said, well, fields are promoted towards fields, and so I wrote about my fields. So E of fields 0. We know also that when we talk about fields, we decompose those fields in terms of plane waves and creation and inflation operators. The plane waves are important. Therefore, I can, in principle, introduce this sort of, if you like, hybrid thing. So let me introduce, instead of this product which sits here, let me introduce something that depends also on the momentum. But this depends only on the coordinate. I know that this can be expanded in terms of plane waves, so I'll introduce the momentum. I'll use some other notations, and I'll try to reduce it here. So my notation looks like this. So let me take this field, and then the fact that it's not exactly this one depends on the momentum. Field here, and I'll say, okay. So suppose I have some sort of transverse coordinate inside of the and transverse momentum associated with this field. Just LT. Okay, now for this guy here, I'll write it's like the same way. So this tilde means that same. I'll have to reduce this, and it will be transverse coordinate Y, transverse momentum M, coordinate momentum. But now, what's the rule to go from here to there? The rule will be the following. So I'll just say, well, it's Fourier transform because I'm expanding everything in terms of plane waves. So for me, if I want to get these fields, some position Y curve, I'll say, okay, so I'll have to integrate this one. Okay, I'll have to integrate this or Fourier transform. So it will be my D2M curve, okay? And the exponent minus I Y curve M curve of this object. Sine tilde Y curve. So I'm using this notation, so I'm not even sure they used in the textbooks. Be mindful, it's just hand waving argument. Okay. So I'm introducing a field which has both coordinates and momentum embedded. So now what I would like to do, I would like to get this by local matrix element, which depends on coordinates. Well, with this rule for me, trivial. Let me get my local matrix element like this. Okay, so from this one it will be X verb, this one will be Y verb, this one. I can shift. So what's important for these things is the distance, right? So the difference between this and that, and therefore I can do here 0, I can do here B, but I can shift to any position provided distance, total distance. I don't want to keep this 0 here. Okay, so it's equal to, and then just by using this rule here, I'll write 3 to L perp to M perp. Okay, so 1 for a conjugate was plus, the other was with minus because 1 is the conjugate. Okay, so that's what happens. Then I have exponent plus I y perp L perp minus I is x L perp. Okay, and this is y minus I y perp M perp. Okay. And then I'm multiplied by this things x perp L perp side y perp M. So many assumptions here, but you get the point. Okay, this one, and now I'm not going to do anything spectacular. I'll just look at the phase. I'll look at the phase of my Fourier transform. So the phase for my Fourier transform is just this. It's x verb L verb minus y verb M. Phase. The phase is important. This. Okay, now the magic of mathematics that I can rewrite it as 1/2 of the sum times the difference plus 1/2 of the difference times the sum. Okay, so it looks like magic, but it's not. And it serves the purpose. So I'm just rewriting it. So nothing here. Just rewriting the same things. Okay, plus 1/2 x perp y perp times L perp plus M. Okay, so now after I've done it, I'll start looking at physics. Okay, so what the physics tell me, then we derived this, showed that this is the right answer. I said, well, this is much in part of this diagram. What's important for this diagram is the forward diagram. There is no momentum transfer between the states. T equal to 0. No momentum transfer, it's T equal to 0 diagram. So no momentum transfer between these states either. Okay? So it means that L perp minus M perp is 0 for the case of team D. Okay, so now team D, this is the generic thing. So once I brought this, I don't know what is happening. Then I consider particular process. I figure this out and I say for team D, L perp minus M perp 0, no momentum transfer. Therefore, this doesn't contribute. Okay. Then I say, well, L perp and M perp is the same, so let me call L perp equals to M perp. Let me call it something. What comes in mind? BT. I'll call it BT. A vector. So X perp minus Y perp will be my BT. And therefore my phase will become AT times BT. Okay, so I haven't done anything here. However, by doing this equal signs and everything, we come to a particular physical interpretation. Because now I say, well, my fields are somehow in the transverse plane, located from this position, they have transfer momentum this and that, they have to be equal to each other in non-momentum transfers of this. But PT has an interpretation now. It's the difference of the transverse positions of this field and that field. While now, those of you who study generalized partner distributions, they will tell me, wait a second, but we use impact parameter for our distributions. Impact parameter would be this. Once you have the momentum transfer, LT minus, so for what is known as GPD world, okay, or GPD world, generalized partner distributions, and that will be the last thing that I will tell you about GPDs, as I'm not an expert, but the momentum transfer, and they call it, is actually L perp minus M perp, okay, and it's Fourier conjugate to 1/2 of X perp plus Y perp to the average position of the quark field inside of the nucleon with respect to the center of mass, whatever we call center of mass of the nucleon. And that is what is known as impact parameter. B. They use some of that. It's 1/2 of X perp plus Y perp. Okay. So this is what is happening if you don't consider this imaginary part, but rather you consider an amplitude where momentum transfer is not equal to 0. In this case, you have momentum transfer, which then will be also here. This momentum transfer will be the difference of the transverse momentum. The transfer the quark fields. And the impact parameter will be 1/2 of the sum with respect to something. And you take this, the center of your coordinates as the center of mass of your nucleon. And that is what is known as impact parameter. Okay. Now, again, looking at this phase, you see that this is not equal to that. So this is Fourier conjugate to this is Fourier conjugate to that, but this is not Fourier conjugate to this, and this is not Fourier conjugate to that. And that's, if you like, a semi-proof that there couldn't be any model independent relations in what we know as generalized partner distributions and transfer. But in models, they can be, because they come from the same relation. Okay, so this is what is concerning physics. Okay, the impact parameter is Fourier conjugate to the momentum transfer, while this, what we call BT, is the distance. Right? How beautiful it is. Think about this. You have a proton moves with the speed of light. And then at some point during this process, you take out work from the proton and you insert it at a different position. And then the proton is happily moving. Well, in real life, it is destroyed. But in our theoretical minds, it's moving. Look at this. Moving, still alive. Okay? The only difference is that quarks were shifted a little bit. And we are looking, oh, we disrupt this situation by shifting quarks. What's the correlation between these shifts? And this is what we're studying. We're studying correlations. So these correlations then would go into this correlation between the transfer momentum and the spin. That's how it happens. That's why, well, but once you take the quark and then you sort of shake it such that the quark fields actually shift. Confinement should know about this, because can you shift the quark field by 20 Fermi? Well, in practice you can't, because where the proton ends, no, it's a 1 Fermi object. In practice, what we do here, I don't say that BT has to be bound by some size of the nucleon, but it has to be very suppressed, and that's why TMTs would be like suppressed at larger words. So confinement has to have an imprint on these distributions because of that. Because you are shifting those quarks inside of the object which you study, and the object is confined within some transfer size. Okay? So this was the physics. Now, okay, so let me leave this diagram here and dwell into 20 minutes. So I have less and less time for actual math. I'll try to do as much. Let me do this physics here. Okay, so here's my diagram. So let me introduce back handbook diagram. There was here. So what I didn't tell you, because I guess many of you noticed, is that this object is not even gauge invariant because I have fields separated by some distance. I can then do translation for this field, parameters for local gauge transformations don't have to be the same, and therefore this thing is not gauge invariant. If it's not gauge invariant, I cannot measure it. Okay? So end of story. Let's go have coffee, right? No, we should be able, right? Because why I would stay here? So how can we restore gauge invariance? In order to restore gauge invariance, we have to remember that there are gluons, and I haven't mentioned gluons at all. It's oh, wait a second. Gluons. They were just introduced by George previously. Quarks color charged, so they like interacting strongly. Okay? And in particular, let me take all those gluons that live for a long time. So they are friends of this quark for a long time. They are friends of this quark for a very long time. They essentially telling me what is happening when I do this sort of interaction. The interaction, well, physically, technically speaking, it's the interaction of the quark which was struck by the photon and the remnant of the nucleon. Because the remnant of the nucleon, now the elephant in the room is also here. Okay. I told you, let me introduce the unit operator. This divide x. Okay. And then everybody's studies quantum theory, quantum mechanics, and we say, yay, we saw it. Perfect. We saw it many times in different incarnations. So come on, just go ahead, right? Only that this x has color. So the question number one, how does x can produce particles there? When I wrote it, I was like, oh yeah, I'm using it, but it has color. Color has to be neutralized. So then we do this all operations. We actually assume that our unobserved state has color. So here, maybe you can get away with this, but then you do permutation functions. It gets more complicated. So whether these states have any overlap for the quarks, the big question. So you have to assume that your states that you produce actually have colors, but they don't. They are because they're hadrons. Okay, so a lot of work to do. We'll not dwell into this. There are ways to deal with this. One of the ways to deal with it is just to include this in the definition. This gluon, which also has color, well, actually too, into the definition of our fields, and then we do this quark field and the gluon field. We call it Mandelstam field and whatever the name, but it's still just a name. Okay. So now let me just get into something. Okay, so one can do some particular transformations. So of this operator fx kt and basically transform this operator using parity in time invariance, and can show that this thing should be like this: f of x kt and st has to be equal to f of x at minus st. Okay, if I imply parity in time reversal, which is the symmetries of st, and therefore my objects should obey this. So now if I look at what I wrote here, I say, oh, perfect. So if I do this, f1 is equal to f1. Okay, perfect. Nothing changes. But here, st will be minus st. And then I say, well, in order for this to be equal to that, I have to say that f1t perp is equal to minus itself, because I still need the minus. I get a plus. In order to get the minus, then I change the sign of st. I'll have to change the sign of f1t perp. Okay, so here's the answer. Okay, f1t perp of x and t is equal to minus f1t perp of x 80 equals 0. So that is a correct operation on this matrix element that reveals that this function has to be 0. And it took 10 years to then understand why it's not. Because if you then measure experimentally the associated asymmetry to this function, it was shown to be non-zero. And the question, we made a mistake somewhere. So, well, we didn't want to make a mistake, obviously, but we didn't take into account something. We didn't take into account this gluon. Okay. So now when we look at this gluon, let me just write some. K, I say L here. Okay, that's the momentum which goes. So here's my propagator. Here will be T minus L, because this chord here I want to have P. Okay. Momentum Q goes in, momentum K goes in, P minus L is there. So I'll look at this propagator only. So what happens with this propagator? The following. So it turns out that for certain configurations, and here what is sitting here is my field. So I'll just say it's A, say alpha at some position Z, which is not 0, so it's between all this and that. Well, actually, if I go from here to there, it goes to infinity. That's my infinity. Okay, so for some configurations with this field, this P minus L squared, okay, can be approximated. Well, first of all, what this P is, so basically it moves in the same direction as Q. So this Q goes into what is known as minus direction. And what I'll write is that, so P itself is on mass shell, so I'll write it as approximately minus 2 P dot L plus L squared. Okay. And then it turns out for certain configurations that L squared is very, very low. Will be just minus 2 P dot L. And of minus 2 P dot L, I'll just pick up 1 P minus L plus. Okay. Minus, because P minus is large, there are all other components small. And then if I write this propagator now, show that I know what's the numerator. Numerator is important. Remember what George was telling. The numerator then gives you the power that is needed in order to get the logarithmic divergence of your integral. Okay, so we'll restore the numerator. That's P slash minus L slash. It's divided by the difference of energies, P minus L squared plus I epsilon. Okay, and P minus L squared. Wrote already here. So it's approximately I over 2 gamma plus, okay, because this is P minus only remains, so gamma plus, that's gamma matrix, divided by minus L plus X. Okay, so this minus is important. And so now I'll start inserting these gluons with plus. So why there? And what you see in this result for the propagator, it doesn't depend on P anymore. So it's not here. It's somewhere here. And then we draw this double line to say it's not there anymore. It belongs to this. There is no dependence on P. I don't have to care about this. Depends only on L, not on P. So it detaches. What this double line is the so-called H-link. H-link is a particular T product exponentiating all this field here in a particular direction. So from 0 to infinity, here it's from infinity to B. Okay, and so this is how it looks like. So I will not derive the whole thing, and I'll just draw how it looks like. Okay. Here. Looks like this. So I have my direction. There's my minus direction there. The work is flying. My perp direction. My one field is sitting at 0. It's this field. Okay. The other field is sitting at B perp. And the other thing is this has some B minus as well, which is for A conjugate to X. Okay. And now I'll insert all these fields. And all those fields gluon fields will live here. Okay. this there, like that. So I insert 1 closer to 0, up to infinity. And then on the other side, I have to do the same operation. Now all my fields will go from this A fields there. Now, as far as I have them very, very close, now my gauge transformations, I can show the gauge transformation of the whole zillions of fields there. And these two fields actually cancel each other, so the whole operator is gauge environment. But I need to introduce those gauge links in order to restore gauge environment. So what was the solution of this thing? The solution of this thing was pretty simple, and it says the following. This configuration is for semi-inclusive deep analysis scattering. For Drell-Yan, I have the same field sitting here at 0 and here at the perp, but now my gauge link will go in this direction. It will come back into this direction. Okay. So the direction of gauge links is pointing to the future because that's where our work is flying. It's flying to the future to meet the detector. Whereas for Drell-Yan, instead of this quark here, I have a quark that goes from here, from the past. It was a friend of the quark inside of the proton from the past, and it annihilates and produces the photon. That's why it is. So the solution is very easy. So here I have just write Dy, here I have to write Cds. Therefore, F1 T perp of Dy is equal to minus F1 T perp Cds. So this one is the consequence of gauge invariance of our operators, and we unambiguously calculated. And that's the prediction of QCD, not only for Team D, but also for collinear theory, because in collinear theory, wait a second, we haven't heard about gauge links, but they have the same problem because the quarks are separated by the distance. So there has to be a gauge link. The only trouble that, well, the only thing is that we don't have now separation in terms of the transfer momentum. Separation only is in terms of minus momentum. And then you say, wait a second, but now all my fields are of certain type. Why don't I take my gauge conditions so that those fields are exactly equal to 0? My gauge condition will be A plus of this field when any position is equal to 0. Therefore, my gauge link, which is the exponent of this field, will be 1. The same trick doesn't work because now I have to introduce two gauge conditions in I can get rid of this one. Then I'll pay a price. I'll have a gauge link at minus infinity or plus infinity. So that's a fundamental property of QCD. If this doesn't work, we'll have to scratch our head very much. Okay. I have half an hour. Right. Let's dwell into it. So what I'll do is that I'll just show the experimental results now. So Drell-Yan experiment. Find induced Drell-Yan from compass reveals this data point. These are predictions if sign of the series functions is changing. These are predictions if sign of the series function not changing. It's just, perhaps 1 sigma deviation. Big question is whether all our measurements at the electron line collider will be able to prove that. Okay, this is one of the projects, if you like working on, you're welcome to work with me. It will take us probably 1 year to figure this out, whether all measurements in the electron line collider or any Drell-Yan experiment will actually be confirmed. Okay, so semi-inclusive scattering, let me not dwell into structure functions, but structure functions are the possibility to actually use angles which are present in our measurements, azimuthal angles of the quadrant and the spin in order to disentangle things. Okay, so for instance, this one will be actually what is generated by series function. So it's relatively easy. Now all structure functions, of course, we don't know the transfer moment of the quark, so we have to integrate them. So this is how it is done. And we have this very nasty, quote unquote, convolutions, because now every KT is convoluted to favorite KT here. This integral is very complicated, if you like. But in PT space, it becomes much easier. So only products are present if we Fourier conjugate this. And we just pay price by particular Bessel function. Okay? So then I was deriving these formulas for our TMD book. For all these asymmetries, they were scattered around the literature, but I don't think there was the total compendium. I said, well, that's a perfect, I told myself, it's perfect time to give a name. So this one is C here, it's a convolution of this integral, so it makes sense. And I thought, what name give this integral? And I think nobody named it. So I decided, let me call B, which is Bessel. Okay. I was tempted to call it P as a product of this thing, and I was thinking, well, but it's also the first letter of my surname. But then I decided, well, let me still call it B. Okay. Let's be a little bit more modest. But the beauty of it is that in the configuration space, it always comes as a product. And I can tell you many beautiful things about this formula, because once you derive it, it's just magic how it works. So all this, well, it's not a magic, but then it's just mathematically beautiful. But we don't have time for this. We have only 25 minutes. What I want to use 25 minutes is actually come back to the derivatives that George was showing. D over D log mu, which is mu over D mu, E over D log zeta. Same derivatives. But now let us do them exactly in the space of energies, not distances. Okay. So then we do these derivatives. So we take our operator, figure out, well, that the answer is not zero. It has the so-called anomalous dimension. Okay, it can be expanded in our phase. So that's all that we need to know about this one. So now we have another source of divergency, because this all comes, technically speaking, from divergences of our integrals. We have another source of divergence for TMDs, because now we have to separate what's moving to the right and what's moving to the left, and it's arbitrary. And therefore, there should be some parameter that tells us what it is. It comes with the name of rapidity divergence, and there should be some parameter that regularizes this divergence. And this is zeta, and this is the so-called Collins-Hofer parameter. Now, if you take this derivative of your operator, you find out that it's a function, but not also a function of PT. It's beautiful. It doesn't just depend on mu, as here. This one doesn't depend on zeta, but this depends on BT as well. Okay? And this function is called Collins-Hofer kernel, which is specific for TMD. It's related to the properties of the vacuum of QCD. Okay, so I'll say a few words about this. But if you just say, oh, it's just a function, so don't worry about this. So this one now can be also derived with respect to mu, and it will have its own anomalous dimension, which is known as Casp's anomalous dimension. Now, for practitioners of TMD physics or perturbative calculations, I think you know a lot about this. For non-practitioners, these are certain derivatives that stem from the same discussion that we had in the previous lecture. The right-hand sides can now be expanded in the expansion parameter of our theory, which will be strong coupling constant. So those are series of coupling constants, even for this one. But this will be a very good expansion if transfer separation is small. Because if transfer separation is small, it's very much collinear. Okay? Okay, and the Z is Collins parameter, this one. Okay. Let me scare you. If we solve these equations, we get this. Okay. So this result here is the solution of TMD evolution equations organized in terms of resummation of, and it has a name, Collins-Hofer surface. Those are people who actually did it. Okay, and then probably if you look at it, and you can say, okay, see you. Okay, I'll do something else. Let's not do this. Let's actually 20 minutes. Perfect. Let's just do it. So I want to show every single ingredient there and tell you how it is derived and where it comes from. I guess we usually don't have this full-blown courses in terms of TMD physics and all that, so might not see this. So I think for any student, you have to suffer at least once and see how it works. Okay. I'll have to do maybe time, but then in my notes, we have all the everything I wrote. Okay, so we'll start from evolution equations. So let's go back to our evolution equations. Okay, and what I'll do first, I'll take the derivative of this evolution equation with respect to d log mu. Okay, so let me do it. I'll write the following. So d over d log mu of my first equation, which is d log of f tilde. Okay. So let me not write what's what the tension of d log square root of theta is equal of d of d log mu of the right hand side of the first one, right? So it's my poles of kernel kappa. It depends on bt and mu. Oh, I know what it is. Well, it's minus gamma k. Good one. So it's minus gamma k. Okay, which depends on mu. So this is equal to that. Okay. So what I'll do now is that I'll swap my derivatives. Dangerous thing to do, but for derivatives it's okay. And I'll say that now my d over d log square root of theta or d of d log mu is equal to minus gamma k. But this d of d log of mu is just the first equation. And it's gamma f. This thing is gamma f. So I know the relation now of gamma f and gamma kappa. And I can solve it. Okay. So let me just write. So this equation is just ordinary evolution equation, differential equation. So it's easy to solve it. So I'll write the answer now for the solution of this one. So it's derivative of this is equal to that. And so it has to be something like this. I'll write for you the answer. In the notes, you will see step-by-step solutions, but here I will not. It's mu zeta divided by e squared equal to gamma f of mu, okay, 1, because at some point I'll introduce my scale zeta 0, and I'll say, let me use my zeta 0 equal to mu squared, and therefore I have 1 here. Okay? And we will have minus 1/2 of gamma k of root log of zeta over mu squared. Okay? So now let me go to here. Okay? 1. That's 1. And sort of get to the other part. So this whole thing is this. So now this 2 here stems from the fact that I have the product of 2 functions. So what I'll be doing, be doing just for 1 function. So in all exponents, you need to get this 2 out and you 2 in. Then you recover that amount formula. So this is nothing else, just anomalous dimensional. Great. So let's solve now equation number 2. This is d log of kappa divided by d log of mu equal to minus gamma k, which depends on mu. Okay. Well, what we do, I'll put d log on the other side, take the integral of both sides. Okay. There's no log. Thank you. I did the right one. So I'll take the, thank you. He'll keep an eye on it. Okay? So, and then I'll write the following. Integral of e k theta is equal to minus integral of gamma k d mu prime over mu prime, which is d log. So this is prime. Okay, and I'll integrate from mu 0 to mu, from mu 0 to mu. Okay, so and I have my solution now. So I can write k tilde of b mu is equal to minus integral from mu 0 to mu d mu prime over mu prime gamma k of mu prime plus k tilde of unity and mu 0. So that's the first solution. Let me keep the solution, but not the derivation. So let's solve the first equation. So the first equation was d log of f, d log of zeta is equal to. So I have this d log of first equation. So just show you this equation. Right. I'm solving. Now arrive at the following. So I have f tilde of x dt mu and zeta equal to f tilde of x dt mu zeta 0. Okay, so the equation is with respect to, oh wait a second, it's the second line there. So in my notes somehow I call it number 1. And I have my exponentiation of k tilde of dt mu log of square root of zeta over zeta 0. So now I know how this thing evolves in terms of this initial condition zeta 0 that I'll have to then fit. So now I have another one which tells me how I run with respect to gamma f basically. So what I'll do is that I'll write the solution f of x dt mu and zeta, and it'll be f of x dt. Now my initial condition here will be mu 0, still here zeta, and then I'll have my integral that this guy's here, gamma. The integral from mu naught to mu of d mu prime over mu prime gamma f of mu prime zeta over mu prime squared. Okay, so these evolution equations are ordinary differential equations. They're easy to be solved. Now the tricky part is physics. So now, first of all, we start from potentially different initial points, first of all. Second, we have at least one of our functions, which is kappa here, which depends on bt, and then bt becomes large. If I'm like 10 Fermi from my nucleon, it cannot be perturbatively calculated. It has to be non-perturbative. And therefore, this evolution in this two-dimensional space, mu and zeta, becomes non-trivial. So what John, George, and Dave did is that they organized the solution in such a way that it gave the most predictive power to the result. Okay, so one can solve these equations, and well, I solved them. I can sort of combine them now randomly, but one needs to do something else in order to make this predictably giving you numerically good results. Okay, so what was done? First of all, they noticed that then bt goes to 0. It's very close to what is collinear, and therefore the operated product expansion can be used in order to expand our function in bt, and bt is very small. Okay, so let me not write mu in zeta. I'll just write the final result. So it is done like this. It's the integral, okay, from x to 1 dx hat over x hat, okay, some calculable function, which is coefficient function, it's a coefficient, g of f of x over x hat, bt, now it depends on bt, and it depends on other things, so I'm not right here, and fj of x mu, fj of x and mu is linear distribution. So what I'm doing here is that I'm doing all this discussion in terms of just Parton distribution functions, unpolarized ones. And I'm now expanding my BT dependence for log BT in terms of this calculable coefficients, in terms of the Parton distribution functions. Okay. So a very good question, what is the relationship between the whole TMD and Parton distribution functions? And I will not be able to go into details of that, but if you have questions, just one of you has a question, come and talk about this. There is an unambiguous relationship between three-dimensional structure and one-dimensional structure. And it's the most intuitive formula that works. Well, but now the question is, now we have this BT, and can go to anything. So in order to partition this space of BT of what is perturbative, what is non-perturbative, CSS introduces a parameter which is called B star. And it's some function that depends on BT. Okay? And this, I'll call it B star, that saturates at some value, which is called B max. Okay? So why it's done, I think it's beautiful. Well, the shape of this function is irrelevant, but they have the shape. So they give us, they say, this is BT square root of 1 plus dt squared over B max squared, give us shape. But well, it's some way of introducing this function that saturates here, so there can be other ways, of course. It has nice properties. Well, nice properties with this. What's important is now if you insert this B star in any function that you write there, you have two things. Well, first of all, this function mostly become perturbatively calculable at any value of BT, because now the B star as a function of BT saturates at some value of B max, and then you will limit your size of B max such that it's not far away from the quarks, so it's perturbative. Okay. So B max is chosen to be around 1 inverse G. 0.2 Fermi outside of the. Secondly, and I think that's the main advantage of this, is that your evolution equations in terms of BT are the same as evolution equations in terms of B star. And therefore, your running of your functions in terms of BT and B star are exactly the same. And you can use it in order to actually separate the non-perturbative parts by actually writing your function in terms of, and we'll actually see how it's done. Okay, so let me start from the first. Okay, so everything is in my notes, so I'll be probably writing very quickly, but look in my notes to get done like that, step by step. There was one type already, I'll correct. We find one logarithm where it was not. Okay, so let's give an example. Okay, so but wait a second. So that's what I want to say. Okay, so B star. Okay, so that is this. So B star is sitting here. So now we are doing this, but now we're sitting B star. So let me now give an example how the separation of perturbative and non-perturbative is happening. So I'll write this. Bt of mu of my Collins-Soper kernel is equal to K of B star of mu, okay, plus K of Bt of mu minus K of B star of mu, okay? And just by definition, the same, because this cancels this one and gives me the same thing. So I have rewritten it. You say, wait a second. So what's the reason for you to do this? Oh, but these things in mu run in the same way. So then I take this difference, they will become independent of mu. So you just take the derivative of these two guys. And by definition, it will give you 0, no running. are running. So this whole thing, I can give it a name. It doesn't depend on mu. I'll call it minus GK of BT. Cool. Minus GK of BT. It's a non-perturbative ingredient in your coordinates of a kernel, which will work out larger BT. Well, now this part here, it depends on B star, it's always perturbative. I have separated perturbative and non-perturbative. Well, now I know how this thing runs, of course, and that therefore I'll write it as K of BT of mu equal to K of B star and mu zero from some initial scale minus my integral from mu zero to mu. Now I have to run it, and the running is happening with the cusp anomalous dimension gamma K prime, okay, and minus GK of BT. So I didn't even tell you what this function is. This function is actually something which is related to the gluons that I draw. Okay, so the gluons will be associated with, say, in Velian, the diagram will look something like this. So it's not a Penrose diagram. It's the diagram where I have my one quark, the other quark, directions. So the fields associated. So they start interacting, and this gives rise to this function. So if anything, there are no quarks there, so only gluons. So it has to be associated with something which is associated with gluons. It was actually shown that this thing is related to the properties of QCD vacuum. So now I'll not give you the proof of it, but I'll just sketch how K tilde minus K tilde looks like. Minus K tilde looks like this. This is how minus K tilde looks like. Does it remind you anything? You look at this function and you think about potential. What does it remind you? Work, anti-quark potential. Okay. So this thing here is my GK. So in models, of course, in models, it's not necessarily that we are extracting quark anti-potential, but it's related to that. Okay. It means we are getting this information about this GK. GK now depends on the gluons, and so it doesn't depend on the process at all. So that's the most process-independent function that you get in CSS formats, and it is related to that. So that's very important. So now, what's the shape of this has to be extracted from experimental data. Beautiful. Okay, so now we can use experimental data, and we is it like proportional to this squared? Is it proportional to log of BT divided by B star or something like this? It's still debates are going about this. It looks like it's linear. Might be squared. So that's where we are at. So now mu naught here, not here. We have to choose our mu naught. And usually, what mu naught is chosen here, mu naught, is taking not from the process itself, but from our B. So because here it's B, what's important. And then it says, okay, let's do mu naught approximately 1 over B star. Okay. Now for technical reasons here, which I'll not dwell into it, so we'll put here not 1, but 2 e to the minus gamma e. After all, we all do MS bar prescription, and that's the typical coefficient of MS bar prescription. It's not far from 1, it's 1.12. So 2e to the minus gamma e, the gamma e is the Euler gamma, but by B star is called mu B star. And that's what this thing then it's promoted. So mu B star, let me just go and point. Mu B star. That's the dynamical scale. Okay, so it sits also here. That is associated with small distances. Small distances give you dynamical scale. It's sitting here, here, and there. Okay, also there. And from this scale, we have to evolve to the scale that we measure. 20 minutes to 20 minutes to 12. Okay. There are two more pages. Now, for those of you who are practitioners, check those two pages, find out all the errors. There might be multiple. I hope there are at least even numbers of mistakes that I did, because the answer is this. Okay. So now trust me, I can prove all this. Okay. So what I want to leave you with is the following. So then George, John, and Dave were deriving all those formulas. My best understanding is that they were not thinking directly of team evolution equations. What the formulas was called, it was called resummation. Okay? And so let me just dwell a little bit into one little piece of this. So let me give you first the names. Okay. So this whole thing comes from the operated product expansion in terms of the collinear distribution. Okay. So now this thing here parameterizes the intrinsic KT dependence of our transfer momentum dependent distributions. It should be process dependent, depends on our target. It's important to figure out what's the transfer momentum dependence, say, of a pine versus a proton. I can talk a lot about this, but I will not. We can talk during our evening discussions if we expect any differences here, and if we expect what kind of differences we do. Now, this is the interesting thing which is related to QCD vacuum. Okay, therefore it's also universal function to be extracted from experimental data. Collins-Overy kernel calculated perturbatively. It's this thing which works at very short distances. We can calculate it perturbatively here. And now all that. Okay, so this exponent here. But this exponent here, where the anomalous dimension of our TMD operator and cusp anomalous dimension enters, is the so-called Sudakov form factor. Okay, the famous Sudakov suppression of the scattering because of the rescattering. Okay. So let me look only at this one. So let's look at this integral at what we integrate and here. Okay. So I'll just sort of extract one thing. Okay. So it's mu b star up to mu q that you call it, but it's just the scale given by the process. Okay. It's just q, the virtuality of our photon. That sets the highest scale. We don't go to infinity for this integral. So it goes to the scale where we measure things. Okay, that was your question. Where we set the scale? Here, the process sets the scale. Where we start from? Well, we can start from anything, but we'll start from where we can calculate it perturbatively. Okay. Now we'll have d mu prime over mu prime. Now let me just write this thing like this. So it's log of q divided by mu prime. I took 1/2 here because it's just one distribution. Okay. The q squared there is because it's twice that. It's 1 plus that for two distributions. Okay. And here's my gamma k. Okay. So I'm not going to evaluate this integral. No, I can, because d mu prime over mu prime is d log of mu. And I have d log of mu here, so it's dx of x. And so this will be proportional in this gamma k, which can be expanded in alpha s. So it's alpha s of the log square of my mu e prime. Okay. Or say mu prime, which I relate from mu e star to q. Okay. So what's important now is that if you go now to momentum space where we actually do the measurements, we will have something like alpha s times log squared of qt, which is the transverse momentum, which will be conjugate to dt. Okay. And the other scale that we have is just q. So now we are doing perturbative expansion. And we say, well, then alpha is a small, perfect alpha is squared, and so on and so forth. But alpha is can be small, but log of qt over q, then qt goes to 0, can be very, very large. Qt equals 0, it's infinity. And therefore, this will spoil any expansion if we do in alpha s. Okay? And therefore, what this formula achieved achieve the exponentiation of all these logarithms. And the exponentiate of these logarithms is there I have exponential of minus infinity. I don't worry. It's just pressing. Okay, so this is this famous Sudakov double log. This is what, in principle, spoils perturbative expansion. Now, the beauty of this sort of logarithms is that in many cases, you can exponentiate the perturbative series for all orders. And once you promote this thing to the exponential, you have the finite result. That's why CSS formalism is such, either initially or continues to be called resummation formalism. But it stems actually from factorization and the consequence of factorization and evolution equations, which we can solve. Well, I didn't make it, sorry, to solve them all. There are only 2 pages that are missing, and produce this result. And then we can compare to experimental data. So comparison to the experimental data, extraction of all these functions will be done by Giuseppe Bozzi next week. With that, my lectures are over. Thank you.
I just wanted to go back to something you said at the very beginning.
Yes.
Connecting TMDs to GPDs can't be done directly. But so my understanding is you start with the Wigner distribution and you either integrate out the transverse momentum or the impact parameter.
Right.
Is there anywhere in literature what happens if you take a Wigner distribution and integrate out the momentum fraction first, to where you could potentially get a 4D and then eventually 2D structure, where maybe not experimentally means anything, but allows some connection to happen between the two?
It's a very good question. So what he's talking about is you have introduced whatever you call 3-dimensional distributions. Okay, so because they depend on X, KT1, KT2. And you're so excited about this because you've been doing it for 20 years. So you learned a lot of tricks. Now you're trying to impress us. But you have written the matrix element that contained basically both. The phase was containing both. And it turns out that not so long ago, like 15 years ago, I guess, people realized that in principle, if we talk about this bilocal matrix elements, we can talk about bilocal matrix elements which will be now 5-dimensional. As far as they are not in Fourier conjugate to each other, we can perfectly know impact parameter and these sort of together. So those functions which are quite known in optics are called Wigner distributions. They're actually 5D distributions. And I completely forfeited all mentioning those. Okay. And the question is now, what is the relationship between these Wigner distributions to the TMDs or GPDs? Yes. So now let me do it completely hand waving, and I don't have it in my slides, but usually people who give talks about TMDs or anything related, they start from this slide, but I don't have it, even in backup. My bad. Okay. They say, okay, we have this X, AT, and now B perp. Okay. So not BT, it's B perp, it's the parameter. Okay, let's call it B. Or even the one which is Fourier conjugate, delta. It's Wigner distribution, so that we don't mix up. So they're 5-dimensional, and okay, well now if we integrate out information about this, so we'll get our TMDs, which depend on F, C, C. Let me get that. B is not BT. So it is what is the Fock parameter. Okay, I'm trying to answer. Okay, so sorry for my wandering around here, but it gave me perfect opportunity to speak. So then they integrate and they say, oh, we integrate of this d to b. We integrate here d dt, and we get some other functions, phi of x now and d. Impact parameter distributions works inside of the nucleon, which are Fourier transforms of what is known as GPT. So Fourier transform. So my best knowledge is once you perform these integrations, information is lost. The question is, can we still find out? So there are proposals to actually measure those functions or calculate those functions on the lattice. So whether we can still bridge somehow through this like this, I'm not quite sure. Let me just mention this. So now we don't stop there. Say, oh, this is like 3D distributions, 5D distribution. So those are beautiful because it's correlations. Those are even more beautiful, I think. But then you go even though in this direction, you say integral of d2 kt, and then you get your linear distributions, f of x. If you think about this, then you perform, say, this integration. So you have d2 kt of f of x kt, and has to give you f of x. Okay. So here in this thing, I have my UV divergence, and I have my repeated divergence. Therefore, it has this mu and zeta. Here I have only mu because it has only ultraviolet divergence, and that's what Ziegler evolution is. So this formula was in 70s. That's the natural thing to expect. So we can reduce from here to there just by doing simple integration. But there are troubles. You have different divergences. You integrate over the whole regions of transfer momentum. In this case, also in the region where your factorization is not working at all, you have to use a different. You have to use gluon radiation. It's not working. So it's magic, but it's working in the way if you introduce an upper cutoff to this integral. Turns out this upper cutoff, and it was shown by at least 3 groups recently, makes this integral depending only on ultraviolet divergence. There is no repeat divergence floating anymore, and so this is actually is collinear distribution. So I think the same things happen in these directions. I have no proof for that. This is actually this integration of information which works. Because then you integrate information, you have to remember that factorization theorems are approximations. They work only in certain regions. So if now you have integrations, you integrate all regions. Therefore, it's highly non-trivial. But still bridging this and this, I'm not quite sure. Maybe I'm not just attentive to the literature.
Yes, just to build on that a little bit, I guess the question that I'm thinking, and I think it's a similar one, is instead of integrating first over either KT or your impact parameter, taking your Wigner distribution, integrating over X instead, so you're left with a 4-dimensional distribution, something like F of KT and B, right? And that might give you something that's sensitive both to essentially a transverse momentum distribution and a GPT at the same time. And whether that might contain an interesting link.
I think it is interesting. Well, this is what, if you like, lattice is doing. Then lattice, you calculate the moments, then you integrate over X, and you have a number. So integration over X may pose similar questions. Okay, so you integrate over X, and what I was doing here, I didn't state it explicitly. I didn't say what are the limits of my approximations. But in principle, if you go to very, very low X, and that's what we are getting next week, evolution equations change. They change quite drastically. And so now if we integrate over X, are we getting the reliable result or not? It's a good question. I think in the same spirit, if you do some certain manipulations here, you might get reliable results. But one should be very, very careful when to capture certain physics. I think definitely one can define those distributions, say these are like impact parameter things, independent effects, integrate, get the results. Similar, like we know for the proton, integrate the Parton distribution functions, difference between up and anti-up quark will give you always 2, because that's how many up quarks we have in the proton in the wave function. What is happening in that? Yeah, I think similar like conditions. Okay, everybody started. It's the time for right? So we have 1 hour help for lunch.
Yeah, so we'll start, we're running late, so let's just go ahead and take a full hour and a half. We'll start at 1:30. And you know it's available at East Dining, you know it's available across the way. On WhatsApp, I posted the places to take the Wolfie card. So across the way, the couple places, the Halal place, Jersey Mike's, 1 or 2 others.